This meeting is being recorded.
All right, ladies and gents. So we're going to get started with our demonstration for class today. We're going to get started with an acid-base interaction video. So what that means is we're going to be looking at a couple few things. I'm going to run over here and grab the clean glassware. Make sure it's dry. Now, for us, what that means for us is we are going to look at testing acids and bases and seeing their interactions. So what I have here is just some basic glassware we have in lab. I have a couple different watch glasses. They're clean and dry and pretty nicely see-through. As you can see, they're good and transparent. I got two of them. They essentially look like giant contact lenses. And I have here a glass stir rod that we're going to use to speed up some things. I'm going to put them side by side so you can kind of see. Let me focus the camera here to see what we can get going. Maybe it's better if I do this. All right, so there is the acid and base interactions. I have with me some universal pH paper. This is the good jumbo kit extra paper to deal with, and it comes itself with a color-coded key to tell me the pH indications. I also have with me some acetic acid, also known as vinegar. This is some acetic acid and a little disposable pipette here. I have some sodium hydroxide, a rather weak concentration of sodium hydroxide, some 0.5 molars. Still should be plenty to do what we need to do. Notice that is good, the initial color of it. Let me see if I can get it to focus. All right, there you go. You can kind of see it down here at the bottom. It's initially a really clear substance. Not too much going on with sodium hydroxide. It's rather unimpressive in the container at least. Nothing too crazy to note. And then we have some phenolphthalein indicator right here. This is phenolphthalein. It's the same situation we have here. It is rather clear in color. I'm trying to get this camera to focus. Trying to be a beauty guru, I guess. There you go. You can kind of see the color down there, nothing too impressive, good and clear. And we're going to get into some discussions on testing for acids and bases. So in class, we've talked about a few different ways to test for acids and bases. You can test using a pH paper, a universal pH paper. You're just going to take a sample of paper. Rule of thumb in Mr. Cole's class is you should do about a fingernail length and you'll be good to go. You don't need a ton of this paper. So I'm going to get a couple pieces just to test our starting solutions. That's the universal way to do it, is to test using those. So I'm going to slide my piece of paper off to the side here and we're going to work out of here. I'm going to test both of our substances. I'm going to test some vinegar on this side, acetic acid. I'm going to do a couple pipettes full down there. And then I'm going to also test our sodium hydroxide here. That sodium hydroxide solution is going to go right in here. Get a good little puddle. Now, obviously, nothing impressive is happening yet, but once I get into testing it, where's my forceps? I'm going to take my piece of indicator paper and I'm going to see what kind of pH we're dealing with. I'll take this indicator strip out here just so we can kind of see what's going on in terms of reaction. So I'm going to take one strip and I'm going to dunk it, give it a little dunky dunk. Give it a second to kind of work its magic, and then we're going to compare here to here. And what I'm doing is I'm trying to match best I can this pH So based on the color combos I see, I'm looking at my best match is probably somewhere in this area. From here, looking at it in class, it looks like it's about a 4. So that's a pH about a 4. So acetic acid is a pretty weak acid. And then we're going to do the exact same thing, but with the other one. I'm going to take it and get a little dunky dunk, and we can kind of see almost instantaneously, get a second to finish doing what it's doing, that we have a difference in color here compared to what I started with. That starting material, the second material is actually quite pretty basic. It's ranging between like a 12 or a 13. I'll go more 12 there because that's a better color match. In terms of universal pH indication, I have a really weak acid and a quite strong base here. And when I'm looking at testing them, universal pH paper is not the only way I can test things. I can also use an organic indicator like red cabbage juice, like we did in lab. You had some red cabbage juice and you dunked it into the pH container. Now, red cabbage juice has a different pH scale than that universal one. A good reference we used in class would be this red cabbage juice indicator chart. We all use these, so we got the same around pH. It's just a good way to match up the colors. Now, it's not as detailed as the other one, but this is a good one. These are available to you in class. You can also use some litmus paper. That's what's embedded in this universal pH paper. It's called litmus. A litmus is a chemical that has a vivid color change in the presence of a pH. Now, if you get more concentrated versions of litmus paper, you'll see it either in two colors, red or blue. Remember, if it's red, that's testing for an acid. If it's blue, that's testing for a base. Or I have another option, particularly with bases, I can use some phenolphthalein. Phenolphthalein has a unique property to it as it has a intense color change in the presence of bases. Phenolphthalein will turn hot pink or fuchsia-ish in the presence of a base. So I'm going to put those on here, and we're going to see what I can make happen in both the acid and the base. I'm going to drop some phenolphthalein in here, and lo and behold, you can't see anything. It's still pretty clear, still pretty liquidy. I'm going to drop in some more just so you can see me do it. Nothing really great is happening of note. Now I'm also going to do the exact same thing here with my base. You see I still got some liquid in there. I'm going to drop it in, and quite instantly I have a really intense color change. Let me put it on the white paper so you can see it better. I have a really strong color change here. And even if I take my glass jar to mix around, make sure I got all that contact going on, I have some pretty intense color change happening that I don't see here. And even if I scoop up some on my glass stir rod and put it in my acid, it kind of just goes away. It doesn't do much. If I get some extra on here and dunk it in there, it goes away. Phenolphthalein has a unique indication in terms of base specificity. Phenolphthalein is specifically testing for bases. It reacts with the hydroxide ions in there and does some other more advanced things that we're not going to talk about in here, but it will react to produce this color change in the presence of a base. Phenolphthalein is base specific. Now, I can also go backwards and make something more acidic by neutralizing briefly that base and producing two new products in a chemical reaction, because this intense color change is a chemical reaction that I can make go the other way by introducing some stronger bases or some stronger acids. So here, comparatively so, I have this purple crap in my watch glass here. I'm going to take a pipette worth of vinegar and I'm going to put it in drop wise. So there's 2 drops, 3 drops, 4, 5, 6, 7, 8, 9, 10, and one more, 11. I have 11 drops in there. So as you should have noticed something, the more drops of vinegar that went in, something was happening here. And that shifted the sodium hydroxide more acidic in nature, so the phenolphthalein had no effect. Had really minimal effect here. I'm going to drop off this here puddle I have into my other one to give it a little wipe out so I can do the next one. And bases come in a variety of flavors or textures, I guess I could say. So we're going to take some off-the-shelf magnesium hydroxide. The brand names will change, but this is the kind of substance you'll use when you have a little extra heartburn going on, called milk of magnesia as a good example of it. Now, take a look at its physical characteristics. It's kind of runny, it's thick, it's white in color. This is our base is what we're starting with. I guess I should put it on the white paper there, Mr. Cole. Now, I'm gonna see what happens if I add in some phenolphthalein. But before I do that, I'm gonna start off with a good basis and keep things the same in my little science demo here. I'm gonna take some universal pH paper and I'm going to do the same. Now, given its name, magnesium hydroxide, I would expect it to have a little bit of a basic nature, and lo and behold, I think I am right. Let me scrape off some excess there. And I got a really interesting blue-green color. So we're going to take the pH scale out, and we're going to try and match it up. Take into account our substance is already pretty white and casty. So I'm saying it's going to sit at right about a 8 or a 9-ish. I feel like 10's a little too blue-purple there. So 8, 9 is a good reasonable guesstimate for universal pH paper here. So it's sitting quite frankly as a weak base. Let's cover up my paper so we don't get no spillage on it. And to validate my results, I can see the color change happen with phenolphthalein because if my pH paper is correct, this should change colors in the presence of a base. So I got some phenolphthalein going on there. Drip, 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 drip. And notice nothing's really happening. Nothing's happening as of yet. But in order for a chemical change to happen, for these chemicals to interact with each other, I have to leverage some facts we know about matter and its materials. I know the more contact I can get a reactant to each other, that's how I can make the reaction happen faster. So that's why I'm going to stir it, or I can heat it up, whatever I can do to get those particles moving faster or getting into contact with each other more often will entice some kind of change to happen. And as you can see, I'm starting to get a good pink color happening, kind of like Pepto pink. As I'm stirring and stirring and stirring and stirring, it gets a little pink action happening here. You can kind of see it on the edge of that camera right there. It looks pink, vividly pink as such. See if I can't get a little bit better contrast here for you. Yo, why is this so exposed? Oh, there we go. So you can kind of see it change to more of a pinky color right here. You can see compared to the white of the paper, you do see some color differential there. And I promise you, in person, it is rather pink. It looks like bubble gum. Pink right here. And I can test it to see if I'm actually still acidic by seeing if I can neutralize that base with extra acid. So let's see, I'm going to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I can already see some stuff happening right here where the color is fading rather quickly. 18, 19, 20, 21, 22. I'll leave it there and see what can happen. Now, to make this reaction happen faster, I'm going to stir it a little bit just to see what I can get involved. And as I stir it, I can see in person that the color change is going away. My things, my bubblegum pink is fading away back to an even white consistency. It's pretty daunting, going away. And what's happening is the acid is neutralizing this base and interacting in a way to perform a neutralization reaction. That's also why in person you can kind of see some bubbling going on here. It's kind of harder to tell on camera, but I do see a little bit of slight bubbling happening here, which is an indication of of a chemical change, much like that color change happened earlier, or indications of a color change. Now we're going to see if we neutralize all of that base with that acid. So I'm going to take some phenolphthalein. I'm going to see if I can't drop some extra in here to see if it reacts. And it does not. And now let's see if I can get a pH reading here. I'm going to cap off this phenolphthalein. Now, to assume I neutralize it all, the products of a neutralization reaction are always going to be salt and water of some degree. Now, sodium hydroxide is a pretty strong base, so we're going to see what that does for me if I've neutralized it all. See if I can't scrape off some of that extra, and I do believe I have. So I should be about even. I've got it just a little touch past pure neutral, which is that green 7. So I'm sitting at around like a 5 or a 6. So I'm on my way. If I added some more in, I probably could get it even. But now that just models for you how acid-base reaction changes its substance fundamentally. I went from an extremely basic solution in here to this almost neutral substance. It shows the dynamic between the concentrations of H and OH ions floating around in solution. Now, in terms of what you can expect in class we're going to establish a mechanism of reaction with this because any acid-base interaction, those reactions that happen, will be between a acid and a base. We're going to say all neutralization reactions have a general layout of being with an acid plus a base yields some amount of salt plus water. And we see that happen specifically in some of our examples we've used in class where I've taken, let's say, hydrochloric acid, what's sitting in your stomach. I've taken hydrochloric acid. You can't really see that one, can you? Mhm. There we go. I've taken hydrochloric acid and I've reacted with it. Let's take what we used in this demo, some sodium hydroxide here. And we're going to see the mechanism that creates the salt and water. So remember, acid-base neutralization is a double replacement reaction. It is a double replacement reaction, which means two cations are exchanging here. So first things first, I have to identify my cations or the positive things in this reaction. Let me get a different color here. I know H has a +1 charge, so I'm going to tell it it's positive. Chlorine has a -1 charge, so that's my negative here. And then, see if I can keep the colors separated for y'all. There we go. Positive and negative, and I'm going to do the same thing over here where I know sodium to be a positive charge as a +1 oxidation state, and hydroxide is a polyatomic ion that has a negative oxidation state. So here we have the basis of what we're going to exchange in that double replacement reaction, where two cations are exchanging partners. So essentially, what I can see happening to make salt and water is I have to make this hydrogen react with this negative thing. Then on the flip side, I have to get my other positive thing reacting with the other negative guy. So essentially, they're going to swap out partners. My cations are going to shift to make new partners. So this hydrogen is now bonded with this, so I'm going to write it in the same color here as plus HOH. That H bonded with that OH. Now we're going to do this thing and see what's going to happen. I got this positive thing trying to attack this negative thing. Remember, we always write positive things first. So we're going to take that and we're going to write sodium. And that my negative thing will be chloride. I'll go through and balance this later. But just so we know, I have made sodium chloride, commonly known as table salt, and HOH, which is another fancy way of writing water, simply because water is two hydrogens and one oxygen. This is just water. So I have done a double replacement reaction to produce some amount of salt and some amount of water. It can be any acid and any base will make salt and water always. This is just a general mechanism of a reaction that can happen here. And we can remember that NaCl is a salt simply because of who it's bonded with. Chlorine sits firmly in the halogens. In terms of halogen families, anything bonded to a halogen member is a salt former. Remember, the prefix halo means salt. That suffix gen means to form or create. So we're taking apart the word halogen here and remembering what we learned back in our previous units. So that's the basis of what we did in class as a science demo. We learned about the physical and chemical characteristics of acid-base interactions and investigations using a variety of methods, whether it's universal pH paper, whether it's phenolphthalein testing for specifically bases, whether it's red-blue litmus paper, or it could even be cabbage juice like you did in lab. It can test for a variety of pH influences, and just so you can see at the top, we have a variety of pHs here going across from what we use just in this demonstration. So it covers a lot of bases here. So if you have any questions, feel free to reach out to me. You know how to contact me. I'll catch you in the next video.